Please welcome Mr. Ramsey as he discusses the future of small UAS avionics.
Hey everyone, I hope you can hear me. I will be pulling up my screen here. Get started. Thanks for allowing me to talk here today. It's a great conference for us. We are, I was asked to talk about future of small UAS avionics, but really nothing here is precluded to just the smalls. You'll see that a lot of this is relevant to up through even urban air mobility vehicles as well. CNS is what we do, so really excited to talk about this. We really focus on CNS technologies and miniaturization and certification of the CNS technologies. And we do that because we believe that is really one of the keys to unlocking, unmanned systems proliferation, whether they're urban air mobility or linear infrastructure or package delivery. It's a key component to all of it. So thanks. Just a quick background on some of the things that we do. We do serve multiple markets. We like to think of ourselves primarily as an unmanned systems focused market because we know that's where the future of aviation is, but we do have quite a few products in manned aviation as well, and products for airports as well. So we have a full suite of products that range the CNS realm. Got a number of certifications under our belt. We're a pretty young company, so we're really proud of this. So I like to show that, that we've, figured out how to certify items under TSOs and STCs and recently under a DoD AIM certification. So like to tout that and beat our chest a little bit whenever we get a chance. I'm going to go through each category just like everyone else did: communications, navigation, and surveillance. So we'll talk about some of the things that we see as important. It's great to be the last speaker because I could get to adjust my talking points as I get to listen to everyone else. So we'll start with surveillance because that's one of the easier ones for me to talk about. Traditional surveillance technologies for manned aircraft. Everyone in this conference is well familiar with SSR and ADS-B. ADS-B's both ground-based and space-based infrastructure, and it provides great interaction with TCAS and ADS-B functionality. So it's a great detect and avoid component. This photograph is a picture of a number of our transponders and ADS-B systems we designed for small SWAP. We designed initially for small unmanned systems, and that allowed us to be very, very creative when we tackled other markets. So we were able to integrate transponders, ADS-B systems, GPS systems into light sockets, right, on aircraft, and it made them very, very easy to install. The two systems on the bottom are our recent unmanned systems certified products. So the one in the middle is a transponder TSO Mode S ADS-B out transponder, not much larger than a couple paper clips there. And then the one on the right is our defense IFF transponder. So this is the realm of what we're talking about. If you've been in aviation a long time, transponders, in the military world can weigh 10 pounds. In the general aviation world, they're a few pounds each, size of a large paperback book. So, we're really driving the paradigm here on small size, weight, and power. ADS-B, Virginia talked a little bit about ADS-B and its restrictions on the use of unmanned systems. It's not appropriate for ADS-B out is certainly not appropriate or allowed any longer for certain unmanned systems per the remote identification rules and changes to Part 91, but there are no restrictions on ADS-BN. ADS-BN is a fantastic element. I'd call it the first layer of defense for detect and avoid. The systems that I showed there that were, the person was holding up something about the size of a couple postage stamps. That was the ADS-BN system for small unmanned systems. And so we like to think that, the best solution is a cooperative airspace. We know that's not a complete reality, but the more aircraft we can equip with ADS-B out, manned aircraft, that makes the detect and avoid job much easier for the ADS-BN portion. So that was a driving impetus for us to approach and enter the general aviation market space. because of companies like Avionics, there are more and more unmanned systems that are incorporating ADS-B in really as standard equipment out of the box. DJI, Skydio are two examples of companies that are incorporating ADS-B in, and other autopilots like the Cube pilot there on the left incorporate ADS-B in as a standard measure. So the more these aircraft equip, this creates a virtuous circle of unmanned systems listening for ADS-B out systems, and the benefits of ADS-B aren't just for air traffic control any longer. So we like to say, ADS-B is drone repellent. So, for those aircraft that fly low altitude, like helicopters, crop dusters, et cetera, equipping with ADS-B out is a great defense against potential collisions. Surveillance also includes a new category called remote identification, and Amit talked about that quite a bit. We talked about ADS-B not being appropriate for most UAS. The final rules for remote identification went into effect yesterday, I believe, right? That places some of those limits on those ADS-B systems. The final rules provide for multiple means of compliance, and that's an important point that I want to hammer on a little bit. Amit talked about the need for interoperability. These remote ID rules do not enforce interoperability, which is one of my concerns with the overall remote identification scheme. In September of 2022, according to the rules, all drone manufacturers need to have a remote ID device, a standard remote ID device output on their drone, and a year later, all operators need to comply. This is the FAA slide. There are actually 3 different ways you can comply with remote identification. You can do so with what they call standard remote ID. That's what they want everyone to comply with in a couple of years. But there's also a concept of a module that is added onto an aircraft. That's the broadcast module in the center. That's a, for lack of a better word, stick-on device. It gives you some capabilities, but it does not allow you to fly beyond line of sight. And then if you are an operator flying within a designated zone called a FRIA, you don't have to have remote ID at all. Navigation side is one thing I want to talk about a bit, specifically GPS-based, performance-based navigation. So undoubtedly, there are lots of pilots here in this audience, and performance-based navigation is a very specific implementation in the world of the FAA. But I want to take those concepts and up-level them to drones and unmanned systems. So here's the ideas, right? All airspaces are not equal, right? So if we're flying at low altitude in the airspace that's shown in the top picture in an urban canyon, you can expect that you may have different performance requirements from your system than if you're flying along the pipeline in open airspace on the bottom system. So we can acknowledge that. That airspace that we're going to fly in is going to demand certain levels of performance from our navigation solution, right? How do we know what is good enough? How do we define those standards? And Andy talked about this a bit, right? How do we define what is good? And almost as importantly, how do we know that we're performing to the level of good as we're performing the operation? How do we know we're meeting that bar? So luckily, the FAA does have a number of parameters in the performance-based navigation component that can help us define what good is. And we often hear how good is your GPS, how accurate is your GPS, but there's way more to the goodness of a GPS than accuracy. But accuracy is always the first one we talk about, so we'll talk about it first, right? So accuracy is the estimated position versus where it actually is, right? But what you may not know or think about too often is that the accuracy figures that you're seeing are a statistical measurement. They are not a certainty all the time. So a statement of 1 meter accuracy for this GPS is meaningless unless you also say it's 1 meter accuracy 95% of the time. And so I tried to show kind of a worst case scenario on this imagery on the right, the orange line depicting the actual vehicle, in this case, a ground vehicle, traversing through some streets, but with the blue line showing the instantaneous position calculation. So you can see that accuracy is not absolute all the time. It's based on lots and lots of different factors. So besides accuracy, you have availability. Availability is, factors of the GPS. Is it, the overall system availability and functional characteristics, right? So do you have access to all of the satellites in the sky? Is it a multi-constellation system? That'll give you a better availability figure than a single constellation system. Your physical installation may block satellites that are low on the horizon, so you're going to end up with lower amounts of availability there. You might be flying in an urban canyon, again, blocking some of those satellites that are on the horizon, and you will have lower amounts of availability. Continuity is very similar to availability, but continuity is the probability that you're going to maintain your availability in a specific phase of flight, once you start that phase of flight. So that's a little bit of a predictive measure as we fly perhaps from an open field into an urban canyon, your continuity may decrease. And then finally, integrity, which is a really important one. We use this word in a generic term quite a lot. I've heard it in briefs today, but it's a measure of trust that we can place on the solution that we've calculated, right? It is the ability in GPS world, it includes the ability of the GPS to actually tell you when it's not performing good enough. And that's a critical item for performance-based navigation. So traditional versus commercial off-the-shelf aviation GPS is a little comparison here, right? So commercial off-the-shelf GPSs are, as Virginia mentioned, they're very cheap. They're not cheap as in low quality, but cheap as in inexpensive. They're designed to give you smooth outputs because they use Kalman filtering. It masks those instantaneous errors that you saw in that imagery. They're optimized for accuracy. A lot of them are multi-constellation. They're optimized for low cost, low swap, but there's no component associated with integrity. It won't tell you when it's not good enough for the particular operation. On the traditional aviation side of things, they're designed to report the output of position calculations. Often they don't have the smoothing calculations because they're looking for the raw position calculations. Unfortunately, right now, the TSO certification standards, they limit us to the US GPS constellation. There's future changes coming that will allow for multiple constellations, but right now they are limited to single constellations. They're optimized for the high integrity, availability, and continuity. Because they're low volume and lots of engineering effort has to go in for the integrity, availability, continuity components, they're often high cost, right? They also include fault detection and inclusion and receiver autonomous RAIM modeling, right? And these are the components that predict whether your system is going to be have continuity, as well as monitoring all the signals from the satellites and saying, oh, satellite 12, looks like it's giving me some bad data, so I'm going to exclude it from that solution. So here's a couple of charts, in terms of the impacts of fault detection and exclusion from Novotel. So in this particular demonstration, the chart on the left, they ramp up the GPS error, the pseudo range error into it. And the chart in the middle will show you what happens to a GPS that doesn't have RAIM and fault detection and inclusion. You can see that we've got position errors being injected in there. And you can see how the chart on the right really holds a steady position error of 0 because it has that FDE capability for it. Really critical for critical operations in unmanned systems. It's not something that a lot of folks are talking about yet. Something that we focused on is how can we have both, right? Can we build a system that is both high integrity and precise and get the benefits of a commercial off-the-shelf system and the benefits of an aviation GPS, and we've achieved that, right? So we have implemented our TSO C145E certified Beta 1 GPS in all of these form factors that you see on the right. So our wingtip and tail mounted transponders include GPSs in them, good enough and certified for ADS-B operations. We have pulled that GPS out into individual form factors and put them in some of the form factors that you see here, so that we can drive autopilots. We can put them on aircraft for other reasons. One in the lower right is a military application, right? One of the coolest things about this, and I'm going to see if, yeah, I didn't have an extra slide on it, but we have enabled a dual position output. So what we've done here is we took the benefits of a commercial GPS. In fact, we took a commercial GPS hardware, very popular brand of GPS radio, and we use that as a raw radio, and we built our own position calculations from the ground up. So now we have a DAL-C, DO-178 software implementation, but that's built off of a commercial hardware component. So we've reduced the cost significantly, increased the safety by adding the integrity components, and we've added a dual output from the system. So you actually get 2 GPS positions from these, from some of these products on the right. You get the integrity position and you get the Kalman filtered, smooth, accurate position. So, you know, we're looking to help drive standards in the future for, you know, performance-based navigation and unmanned systems. Leaving GPS behind, I wanted to talk briefly about autopilots. Autopilots and flight control computers really carry the entirety of the burden of the autonomy of the aircraft. These things are not equivalent to their manned aircraft counterparts. Hector mentioned fly-by-wire systems. These things control multiple rotors or no rotors. They control payloads, they control interfaces to avionics, and they are significantly complex and fantastically performing. And if these technologies didn't exist, we wouldn't be where we are in the industry today. They range from open source models to, you know, fully professional military grade platforms. How do we certify these things, right? There is no certification basis for this. How do we quantify its performance? How do we make sure that something that is infinitely configurable, like the open source models, are sort of locked down into known configurations? This is a huge problem, an interesting problem that we're going to have to figure out how to you know, address. More of an open question for this workshop, and you know, I don't have an answer for you at the moment. Moving into communications, Virginia talked about CNPC quite a bit, right? So I'm gonna repeat some of what she said here. But in 2019, there was a research study by the UKCAA. Really found that over a quarter of the drone users had lost their drone. Usually, of course, these are all sort of hobbyists or consumer drones. Almost always because of flyaway scenarios, lost link scenarios. There was a really interesting recent AAIB report in the UK about a flyaway activity that recently occurred with a 95 kilogram drone. It flew vertically upward into Heathrow's airspace where it depleted its battery and plummeted 8,000 feet and landed about 60 meters away from some houses. The photograph you see here are the C2, some of the C2 components that were on that platform. There's no business having a 95 kilogram drone with a, you know, a breadboarded C2 system here. So C2 is a critical component of the overall aircraft, both in the quality of the radios that are being built and the protection of the frequencies that are being used. So now there's more, pleasingly, there's more of a trend towards certified and certifiable systems. We're looking at type certifications on larger platforms. We're looking at what types of frequency spectrum we can use. We're looking at the specific radio functions. We're looking at redundancy, and we're looking at you know, minimum performance standards of those radios as well. Current state of affairs is about 95% of all unmanned systems are using unlicensed frequencies, and Avionics has an unlicensed frequency. It's the device in the center here on the upper right, the little silver device. That's our ISM frequency radio. But I think everyone in industry and the regulators see this as a risk and desire to move towards some protected spectrum frequencies. Virginia talked about how the C-band has been allocated by the World Radio Congress and is being flowed down through ICAO to local regulators for more risky operations. In December, RTCA published DO 362A. That will be the certification basis for TSO called TSO C213A for CNPC, and multiple manufacturers are working on the development of C-band radios that will presumably meet C213A. Sorry, I think I said C. We are working on one of those radios. We're one of those manufacturers working on the C-band radio, and that's the device that you see on the lower left here. This is a C-band radio, a 10-watt radio that we are working on right now. We expect to be flying this summer. Hopefully, if the FCC and the FAA publish their TSO and service rules, we will have an ability to certify this device early in 2022. But is a certified radio in itself enough to make a safety case? And we don't think so. So I'm going to come back to the ground component here, right? In areas where terrestrial infrastructure, including multiple ground radios, are required, we believe that the entire infrastructure needs to be managed as a part of that safety case. We're developing a prototype system that we've called Skyline. We are deploying it in North Dakota right now as a part of their Vantis Fly UAS beyond visual line of sight statewide network. And Vantis, or Skyline, sorry, it's really what we believe is the first enterprise command and control infrastructure management service built from the ground up to meet aviation standards that are going to be critical to UAS and UAM. It focuses, it's built on its core of certifiable and certified hardware, but managed by a certifiable network layer of services that monitor the entire network and make adjustments as needed. As I mentioned, we're deploying in North Dakota. We recently announced that we're also deploying in New Mexico, Canada, and also soon in the UK as well, this network. It's a scalable infrastructure. It's meant to be point to point if need be, but it can scale for linear infrastructure, wide area networks, et cetera. So some of the things that this system does is manages the statistics and the health of the underlying network, the backhaul network, the RF links, the redundancy of the radios. It monitors the signal strength. But as a part of a UTM system, as a USS system, it is also aware of the future flight path of the aircraft, the next milestones, and it can manage frequency and handoff capabilities in a make before break manner before releasing the signal from the radio that's behind you to grab on and obtain a firm lock on the future radio. We recently demonstrated that capability up in North Dakota. As we move forward, Virginia also talked about the need for dynamic frequency allocation. Our radios are already pre-designed to be allocated multiple frequencies in the bands that they're meant to be operated for. So we expect that in Skyline, we will be implementing a dynamic frequency allocation functionality as we move forward there. So I think I probably have run out of time, so I will stop there, but happy to take questions.